Inside most nuclear reactors, water does far more than cool the core. It slows neutrons, controls reactions, transfers heat, and in many designs, the entire reactor depends on it. Remove the water, and the physics itself begins to change. So today, we ask a deceptively simple question. Why do nuclear reactors need water? Inside a reactor core, nuclear fission releases an enormous amount of heat. That heat must be removed continuously. Otherwise, temperatures begin rising extremely fast. Water absorbs this heat and carries it away from the fuel. In many reactors, that heated water produces steam, and the steam spins turbines to generate electricity. A reactor without cooling is not simply inefficient. It becomes unstable. But cooling is only part of the story. Inside many reactors, water also controls the nuclear reaction itself. When uranium atoms split, they release neutrons moving at very high speeds. But these fast neutrons are surprisingly inefficient at sustaining fission. So the reactor slows them down. And water helps make that possible. As neutrons collide with water molecules, they lose energy. They become slower. And slower neutrons are far more likely to trigger new fission events. Inside many reactors, water is not just carrying energy. It is controlling probability itself. So what happens if the water disappears? In many reactor designs, less water means fewer slowed neutrons. And fewer slowed neutrons can weaken the chain reaction itself. This effect is known as negative feedback. As conditions become unstable, the physics pushes back towards stability. But reactor behavior depends heavily on design. Different reactors respond in different ways, which is why reactor engineering is fundamentally about understanding physics, not fighting it. Water is not rare, it is not exotic, and yet it became the dominant material inside most nuclear reactors on Earth. Because water does many things remarkably well. It stores heat efficiently, transfers energy effectively, and moderates neutrons naturally. It is abundant, accessible, and deeply understood by engineers. Water became dominant not because it was perfect, but because physics favored it. Inside a reactor, water is doing something extraordinary. Invisible particles collide, heat moves silently, physics balances itself moment by moment. And beneath all of it, ordinary water holds the system together. Not through force, not through complexity alone, but through the quiet logic of physics itself. This is Reactor Atlas, exploring nuclear energy through physics, not fear.